This frequency code is something I've never wrapped my head around. How they do it exactly.
I also never wrap a comb around my head.
Good afternoon, good morning, viewers. This week we are talking a bit about the new results that have been released on the archive. It's about new atomic clock measurements where they're claiming they can measure general relativistic effects across a millimeter. This is the paper in question. It's from Jun Ye's group, which is famous for doing atomic clocks at Gila at Colorado University. So I'm going to talk to you about basically the background of these new atomic clocks and kind of the new results. So let's get into it. So firstly, I think we all know that relativity affects time, right? So there's this famous effect of time dilation where if two observers, they're moving relative to each other, then the clocks of the moving party actually tick slower than the one that's stationary. So the lady in the spaceship here, her clock is ticking slower, meanwhile the guy on Earth is aging rapidly, right? So this is time dilation due to special relativity, but there's also this effect which is called the gravitational redshift, which is that the time slows actually as you are closer to a gravitational body, like a large mass. So this is a kind of an extreme example of if you're near a black hole. So if you are outside the black hole, then time is ticking along. But then as you go closer and closer to the black hole, and if you're at the event horizon, then time freezes at this point. So this is an extreme example where general relativistic effects actually affect time in a very severe manner. So actually you don't need to have this kind of extreme regime to see this effect, and people have been looking at measuring this effect for decades now. So there's a famous experiment by Hafel and Keating, I don't know how to say it, but this was in the 70s, and basically what these guys did was to load 4 cesium atomic clocks onto an airline, just a regular commercial airline, and then fly around the world, first like east-west and then west-east, and then they compared all these clocks to the clock that's on the ground at the United States Naval Observatory, and then they were checking for these relativistic effects. And basically the results, the upshot of this is that, so if you look over here in the table, eastward is like, that's the direction that the plane is going. These numbers in the table here are showing the predicted time differences to the stationary clock on the ground. So there's 2 effects. There's the gravitational redshift, the one that I was talking about earlier, and also the kinematic, the special relativistic effect. That's just the movement, time dilation due to the movement. And so if you add both of these together, then you get a predicted amount. And this is what they actually experimentally measured. And so you can see it agrees pretty well. What you notice is that these numbers are kind of different for eastward and westward. And this is basically because the plane is either going with the rotation of the Earth or it's going the opposite rotation, right? So you get different amounts here. These are roughly the same because the plane is basically the same altitude either way, going eastward or westward, right? So they got pretty good agreement with that. So, this is from 1971. More recently, Japanese group did an experiment that was measuring just the gravitational redshift. So what they did was to put two clocks at the Tokyo Skytree. You guys have been there. So one at the observatory deck, probably here. I think there's 2, and then they also put one down the ground here, and basically compared the rates of the clocks ticking for both of them. Right. This is the guy Hidetori Katori. I've met him a few times, and basically what they found is that like the the clock that's on the observatory is actually ticking 4.3 nanoseconds faster per day. And so they can measure this using their clocks. So, you can really measure these things, and it's actually very important to take these effects into account, because things like GPS, if you don't take into account of these effects, then your GPS systems don't work at all. Okay, so how does atomic clock actually work? So this is basically how it works. So the old kind of technology was based on cesium atomic clocks. And basically what you want to do is you want to extract the light that's tuned to a particular transition between atomic levels of cesium. So the good thing about atoms is that they're all identical and they all have the same transition frequency. And so the 1 second, as we've got it defined now, is defined to be 9,192,631,770 oscillations of the light that's emitted by this cesium atom. So this light that's coming out of this particular transition, the trick is to use that light and to multiply it by some number, and that's your definition of a second. And how you actually do this in practice goes something like this. So you get a bunch of cesium atoms. You first filter it so they're all in the lower energy level. And then you got this microwave generator that's got a knob here that you can tune the microwave frequency coming out. And then if you get it exactly at the right frequency, then it will flip the atoms into the excited state, say this n=3 state. And basically here we've color-coded it so that the orange ones are in this excited state and then the blue ones are in the lower state. And if you get it at exactly the right frequency, then all these atoms will flip, and then you'll detect all the atoms in orange here. Now, if for some reasons, your frequency generator starts to drift, you'll be able to detect that in your detector, because sometimes you're going to get a blue atom here. And then so as soon as that happens, you can use a feedback kind of circuit to shift your frequency back onto the correct resonance frequency, and then you get it exactly at the right frequency to flip all the atoms into orange. So that's how traditional atomic clocks work. These types of clocks are, say, typically accurate to 1 second in 6,000 years, which sounds already super good, but actually by today's standard, that's actually really nothing, because these clocks are getting more and more accurate. This is the fractional frequency uncertainty. So this is basically how accurate your frequency is as a relative number. And you can see that these cesium-based clocks are now being overtaken by these optical clocks, which are kind of a more recent invention. And basically the only difference here is that instead of using a microwave transition, so remember this frequency here, 9 billion something hertz. This is 9 gigahertz, right? And 9 gigahertz light is in the microwave regime, right? But these new clocks are now using optical frequencies. And basically, if you use optical frequencies, there's a kind of a fundamental advantage in terms of clocks, because basically your clocks are kind of ticking faster, and so you have a kind of a higher resolution of your clocks. And so now these days, the optical transition-based clocks are now beating the traditional microwave transition clocks.
It triggers me that it just keeps going down. Yeah. It scares me.
Like a Moore's law.
Yeah.
You should name it after yourself.
This is like Marek's law.
Marek's law. Okay, you heard it first here.
Yeah.
So this is basically that's stated as a formula. So this is the fractional uncertainty in the frequency. Basically what this formula tells you is that what you want is a very small line width of the transition. So you use very narrow line width. Use as high frequency as you can. So this is where the optical versus microwave comes in. So the larger, the better, because this is on the denominator. Also, the more atoms you have, the better too, because this is the standard quantum limit, basically. As for the next generation of clocks, there's several different types of technologies. This first one here, the cesium fountain clocks, this is based more on the traditional microwave frequencies, but these new ones here on the right here, the atom trap clocks, the optical lattice clocks, these are using the optical transitions, and just a matter of different kind of species. So ions obviously use ions in order to the frequency of the transition. Optical lattices use neutral atoms. But one big difference here is that optical lattice uses a large number of atoms, whereas this one actually uses only a single atom. But otherwise, basically, it works more or less the same as the old cesium clocks, but just using these optical frequencies. So here's your transition frequency. This is the laser that's trying to cause that transition. Here's the feedback loop in order to see how successful you are in creating that transition. And basically the technological development of these is that you can use these things called frequency combs in order to measure these optical frequencies much better. And this is what you couldn't do before that you can do basically now. So the main sort of problem here is that the light frequencies are extremely high frequency, and so it was difficult to mesh them with conventional, say, digital electronics, computers running at gigahertz. All right, so if we go on to the actual results of the experiment, this is basically what the group did. They have an optical lattice in this kind of vertical direction. Use strontium-87, there's about 100,000 atoms, cooled down to 100 nanokelvin. Firstly, I think one of the kind of technological developments of this is that they can have extremely high coherence times between these optical transitions, so that they could measure very long coherence times, somewhere in the vicinity of a minute. This is a Ramsey spectroscopy experiment. And basically what they're trying to measure here is frequency difference between two clocks that are at different heights. So this is the relativistic prediction that you would get some frequency difference proportional to A is the acceleration due to gravity, H is the height difference between these clocks, and then C is the speed of light, of course. If you plug some numbers in, then per millimeter, you expect actually a change in frequency of about 10 to the minus 19, a relative change of frequency. So this is basically what they're trying to measure. And this is the data that they have. And okay, so firstly, this is the fractional frequency that they are measuring. And this x-axis is the relative height across the sample. So basically this whole setup is about 1 millimeter across, right? Basically, if you're lower or higher, there's a difference in this relative frequency between clocks that are ticking at the lower end of the sample rather than the higher end. And so the green is showing just the raw data. The gold is, these are some kind of systematic effects that they have to sort of take care of. They can explain some systematic effects such as the second order Zeeman shift. And the purple is like the process data taking into account of all these systematic effects. And so the black line is actually the thing that is the more or less the final result. So you can see that there's some kind of slope here. It's a bit hard to see, but there's some slope to the data. Obviously, this is averaged over the full data, and this slope is basically the thing that we're actually talking about. They repeated the measurement over several days. Looks like about a bit over a week, and basically measured that slope on every day. And the red line here is the expected frequency difference. So that's the theoretical estimate. The black line is the average of all these purple points, and the dotted lines are some error bars on it. So you can see that the experiment matches quite well with the theory. And finally, basically to measure this, you can imagine you need unbelievably stable clocks. So this is also apparent in terms of the fractional frequency uncertainty. They're really kind of pushing these clocks towards unbelievable levels of accuracy. This is a quote out of their conclusions, but they're saying it's nearly 2 orders of magnitude better than previous estimates. So that's it.
I have a question. So in quantum clock synchronization, do you need to assume the clocks have same frequency? And if yes, then can we deduce that this affects quantum clock synchronization because they would not have same frequency if they're at different heights?
Yeah, that's a good point. Yeah, I defer to Ebube because it's his paper. Yeah.
So that's an interesting project idea. Quantum clock synchronization immune to
gravitational redshift.
Yeah.
Well, I think even in synchronization, I think that's the kind of thing you really want to get.
That's the objective.
Yeah, because all these things that are causing the drift or they run away of the time is what you are trying to somehow correct when you do synchronization, because your clock has drifted somehow.
Yes.
You are sort of trying to bring it back to make sense of bring back the second half where it should be or something like that. So
imagine you sit in front of your future computer, you move it by 1 millimeter, and your thing just broke because
yeah.
too precise. Yeah.
Well, this is where you really need the clock synchronization. Yeah. Because every clock is going to have a slightly different gravitational field.
Maybe we could produce artificial rooms where you have flat space-time just for the computation purpose.
Yeah. Yeah, wow. Yeah, imagine that.
Future server rooms.
you just said that the cesium clocks lose a second in 6,000 years. So why do we really care about this new clocks? I'm just generally speaking, I don't know. So if I'm losing 1 second in 6,000 years, so I've made a very perfect clock so that in the next 6,000 years, let the next person correct it, right? So,
yes.
So I don't know.
Well, I think so. Beyond obviously, we're day-to-day use, just using even our phones or whatever. It's perfectly good enough to survive day to day, right? So I guess the applications are kind of for more kind of exotic things. And so, what they say in the abstract here is that, you're getting to the point where this is a general relativistic effect, right?
Mm-hmm.
To see this over 1 millimeter. So basically what you're saying is that you're seeing a general relativistic effect over a distance of 1 millimeter, right? And then, well, firstly, there's all kinds of questions of combining general relativity with quantum mechanics, right?
Yeah.
So if 1 millimeter is actually getting to be kind of a quantum mechanical scale, right? You can have wave functions of 1 millimeter if they're kind of big. So I guess there's sort of some interest in terms of that. And then I also heard some things said, like my old supervisor, not my PhD supervisor, but my honors supervisor, I heard him say in an interview about this work that perhaps you can use this to measure like variations of fundamental constants. There's this like whole talk of how alpha, this fundamental constant alpha. Fine structure constant. Yeah, how alpha might have changed through the history of the universe, right? And so maybe like if you have such precise clocks, then you could actually measure this alpha changing, like not over like billions of years, but maybe like like a day or something, because the clocks are so precise. I don't know. So like applications like that, and maybe you could like use the clock to navigate through space time or something. I don't know. Is that crazy? I mean, because basically your clock is then now telling you like the gravitational curvature like of space time, basically, right?
So
I mean, that's basically yeah.
For the navigation device.
Yeah.
Spaceship, right? Atomic clocks.
Oh, satellites, yeah.
Yes,
And GPS satellites.
Yes, they do have it on satellites. But how?
But they cannot read time remotely using clock synchronization.
No. I don't think so. Well, actually, I think those GPS clocks, I think they're synchronized also to the naval clocks themselves.
Right, yeah.
I think that's somehow. So, once in a while, I think the naval clocks are the master clock actually.
Yeah.
So once in a while, the GPS clock is being synchronized to the naval clocks. And I think, okay, for instance, that might be a very good reason why they're doing this. For the GPS clock, I think it might be affected by something like this gravitational redshift, for instance.
Yeah, of course.
Because it's up there orbiting, or I don't know, whatever it's doing up there. But
Whatever it's doing.
So my computer clock is like just quartz oscillator clock.
yeah.
Once every how many thousands of years do I have to sync it?
Probably quite often, actually.
Exactly. Because it's like, for instance, I don't know who synchronizes it, but I think Windows, like for instance, one might be Mac that will be synchronizing it every now and then. Because I remember that some of, like, okay, for instance, in Nigeria, when I was in Nigeria, I don't really have internet that regularly. So sometimes, when you hear BBC, I forgot their jingle, and they mention the time, you look at their computer clock, it might be maybe a minute or two, or even 3.
Are you sure that's the reason?
Or faster. No. But when I came here, I noticed that when I listen to BBC again and look at my clock, it's always,
But maybe it's because the time flies fast when you're having fun.
No, it's not that. Like I told you, I don't have access to internet in Nigeria.
Oh, so you can't have fun without internet. It all makes sense.
Good point.
It all makes sense. I understand what you mean. Yeah.
So that's the thing.
I think everyone has this kind of experience. If you have a computer which is not connected to the internet for a very long time and you reopen it again after a few years, there will be a obvious time lag.
So if you're late to work, you can say that, sorry, but I didn't synchronize my clock. And you know what's another weird thing? Every time I look at my watch, it's 11:11. Why?
Out of hour.
Yeah, that's crazy.
Wouldn't this have been contributing to the accuracy of improvement that are getting over the cesium ones? I mean the cone.
The cone. Maybe. Yeah, I don't know. Could be. Yeah, I don't know. You might be right, but maybe that's just fundamentally more accurate. Also, yeah, might be, but I'm not an expert.
I'm not an expert. In fact, I don't really. This frequency cone is something I've never wrapped my head around. How they do it exactly.
I also never wrap a comb around my head.
Okay.
Can we have a weekend, please?
Okay, I think the weekend is going to start now. All right. So thanks everybody for watching, and we'll see you for the next video. Bye.
Bye.
Bye.